Hello and welcome to another video in this series as we journey from the very simple primes to the foothills of the Riemann hypothesis. This is actually part 2 of a video that we started last time where we looked at the primes, or specifically the gaps between primes, and we asked ourselves the question, are the gaps constrained in some way? Because we saw how the sum of prime reciprocals diverges, which means they can't be, the primes can't be too far apart. And we also remembered that Gauss discovered that the primes are, well, they have a sort of a density which is 1 over log x, and that's the prime number theorem. So that suggested there were constraints, but actually we proved surprisingly that actually prime gaps can be as large as we require. There's no upper limit. That led us to think about, well, how can they both be true? How can we have prime gaps that are as large as we like, but also have an overall density that is 1 over log x? And we concluded that the only answer to that must be that large gaps are rare. They do exist, but they're rare. And then we looked at this chart, this graph last time, which is a distribution of the prime gaps. We saw that smaller gaps occur more often, and the bigger the gap, the less frequently they occur, which kind of makes sense intuitively in some sense. This chart actually is for all the gaps up to 500 million. And we were struck last time by how constrained this distribution is. It's a very linear shape. It's a very kind of a narrow band. There's nothing kind of above or below. And we thought, well, is there a theoretical foundation for this? And the reality is that just like the distribution of primes themselves, the distribution of prime gaps is just beyond the reach of mathematics in terms of being able to be described in a simple kind of way, in a simple formula. So today we're going to look at a slightly left field approach to prime numbers, which is to use probability and see if we can use some of the ideas there to model this this distribution. The use of probability in studying primes is actually quite sophisticated and I guess a little bit advanced as well. But we're not going to do that today. Today we're going to just keep things really simple, just to get a taste. But if you want to read more about it, you can look up Harold Kramer, who did a lot of the kind of work in establishing probability applied to primes as a field. And what's useful about that? You might be asking, well, why is this useful at all? Because probability is very, approximate. We make simple assumptions. The usefulness of it is that the results from a probabilistic approach seem to match, or can be made to match, experimental data fairly well, or even really well. And what that means is that the results become conjectures which have a lot of support, evidential support behind them, and then are worthy in terms of pursuing and trying to prove them properly. So it's quite a nice machine for generating interesting conjectures, and we might come back to that at a later stage, and you're certainly welcome to kind of read more about it. There'll be some links in the blog if you want to do that. So today we're just going to build almost the simplest possible probabilistic model and see if that kind of brings us any useful results. So to start with, and this is the core idea really, we start with the prime number theorem, or even Gauss's observations, that the density of primes around x is approximately 1 over log x. Now this was proven as part of the prime number theorem, so there's the reason for believing it, and it's truer for larger and larger x. It's asymptotically correct. Now, thinking about the density of primes around x, it's not such a big leap to then interpret that as a probability, interpreting the density the higher the density, the more likely there are to be primes around X. Now, we have to kind of lose the scaling a little bit because a proper probability distribution has to sum to 1, and we're not doing that here. So you can think of this as a relative probability. But the core intuition is that the lower the density, the less likely there is to be a prime, and that's the basis on which we're going to build this model, and in fact many models are built on that as well. So let's think about a prime gap of size 4, just to get started. And a prime gap of size 4 means that we have a prime and another prime, but in between we have 1, 2, 3 non-primes. So that's the sequence, that's the gap in between. You might remember there's some differences in how you define a prime gap, but the consensus is that it's Pn plus 1 minus Pn is a prime gap. So this is a gap of not 3 but 4. So the important point is that a gap of size 4 is a sequence prime, not prime, not prime, not prime, prime. And the probability then of this sequence happening is a probability of prime times a probability of not prime times a probability of not prime times a probability of not prime times a probability of a prime. So that is 1 over log n, which is that one, 1 minus 1 over log n plus 1, which is, so the probability of this being prime would be 1 over log n plus 1, but 1 minus that is probability that it isn't prime. Similarly for this one, we've got 1 minus 1 over log n plus 2. Similarly there, and the last one is a prime, so it's not 1 minus, it actually is 1 over log n plus 4. So that looks a little bit cumbersome, but at least we've encoded this probability. Now, this does assume that the events, this chain of events, the events are independent, and that's something we're going to roll with for now as a simplification. You'll realize actually that there's quite a few assumptions and simplifications that we make in order to make the kind of theory manageable, but the surprising thing is that we get some interesting results anyway. Now we can clean up this this horrible kind of algebra by making an approximation, which is, if we look at the form log n plus a, if n is much larger than a, then that's approximately log n. You can do that by expanding it out, or you can just do it experimentally to see it, but it's it's a flattening function in some sense. So the log of n plus a, where n is much larger than a, is approximately log n. That means all these, log n plus 1, plus 2, plus 3, plus 4, we can just simplify them to just log n, as long as we then assume n is large. So that's another assumption we're going to add to our list of assumptions. So that's a much simpler formula now. It's the probabilities of 2 primes, so that's squared there, and in between we've got 3 non-primes, that's why there's a 3 there. Okay, now if we think beyond just a gap of size 4, but think more generally to a gap of size, say k, the same steps give us a sequence that is prime and another prime, but in between we'll have k minus 1 not primes, and that will give us a probability of, again, 2 primes at the end. So that's the probability of a prime and the probability of another prime, and then there's the probability of not being prime, k minus 1 of those. So that's the expression for the probability of a prime, k minus 1 non-primes, and then another prime. That is the probability of a gap of size k. Right, now this power is making us think, well, we should perhaps take the log of this, but not just yet. Let's let's see if we can extend from the probability to an expected count. So when we know the probability of something happening, we can work out or approximate the expected number of gaps. So for example, if we take a simpler example, if we think about coins, if the probability of a coin being a head is a half, if we have 10 goes, then a half times 10 is 5, is the expected number of heads. It's the same idea. The expected number of gaps of size k is the probability of the gaps of size k applied for all the n up to an upper limit, say capital N. Now we are making some, again, simplifications around the start and end of that sequence, but again, when n is large, this capital N, it doesn't matter so much. So if n is say 1,000 or 1,000,000 or 500 million, then the fact that we might have some edge effects doesn't matter so much. What do I mean by edge effects? I mean that if I have a gap of size 10 and I start the gap just 1 or 2 from the end of that sequence, I'm going to overflow, but that's a small factor. It doesn't matter so much. So there's another simplification we can make here, which is for most n between 1 and n, the logarithm of n is approximately log n. Let's actually see why that is. Let's write it out with pen and paper. So if we have a number range from 1 to capital N, and n can be anywhere in there, what we're saying is that the log of n is approximately log capital N for most of the n in that range. Why can we say that? Well, let's just imagine that n is halfway, it's n over 2. So the log of n over 2, capital N, is log n minus log 2, and that's a small number. So even halfway, we're almost at log n anyway, with just a small difference. And as n gets bigger, this becomes even more insignificant. So making that approximation, that log n is approximately the upper limit, log of capital N, we can simplify this sum of probabilities to n times the probability. And this one is now the expected number of gaps of size k. So actually, now let's take the log so that this becomes a multiplication rather than a power. So if we take the logs, we have the log of the count is k minus 1 times something plus some little things there, some constants. And this is linear in k, so we should expect a straight line. And in fact the gradient should be negative, because the gradient is this thing, because if we have a line of the form ak plus b, then a is this, and that's 1 minus a small amount, so this is always less than 1, so the log is always negative. So we should expect a straight line which is falling. Let's plot that, and this is what we see. So the blue dots are the actual counts of the prime gaps with the log taken, and this reddish line is that prediction, and it's not bad. For smaller primes it seems to be a little bit more accurate than the very large ones, It's certainly going in the right direction. The order of magnitude is about right. It's, it could be a little bit better, I guess. If this kind of intersects the y-axis at say 18 perhaps, and this one might do as 16, that's okay. It's not amazing, but it's not a disaster either. So overall, this very simplified probabilistic model of the primes has given us this prediction of prime gap counts that is not bad. Not bad, especially given the simplifications we made and the approximations we made. Let's see if we can improve it a little bit. Again, we're not going to do anything too advanced, just a little small improvement. And the small improvement is going to address the fact that our simple model, our ultra simple model, ignored the fact that even numbers never prime. That's quite a thing to ignore, isn't it? Because every other number is even. So what can we do? How can we improve our model? So let's go through the thinking steps. If we want to assert that every even number, the probability of it being prime is 0, but at the same time we want to preserve the prime number theorem, which says the density of primes is 1 over log x around the neighbourhood of x. If you want those both to be true, that means we have to shift the probability that would have been on the even numbers onto the odd ones. I'll correct that, that should say odd. There you go, corrected it, magic. So we're shifting that probability that would have been carried by the even numbers onto the odd numbers so we can double it. So that overall the density of 1 over log x, which is over a neighbourhood of x, is more of a global statistic, is preserved. So that's a simple thing we can do. That means we can follow the same steps and arrive again at the same, we can arrive at a probability of a sequence with gap size k. In fact, let's do it with pen and paper. So we have a sequence of numbers, and we're saying that we have a prime and prime there, let's say, and these are not prime, not prime, not prime. But we're also saying that the even numbers can't be prime anyway, so the probability of those is 0. And the odd numbers could be, so they do have a probability assigned to them. And we said that that probability is now 2 over log x, because we're compensating for the fact that every other number, the evens, are kind of cancelled and they don't have any probability now. So this time when we say we have a prime gap of, say, size k, we're actually only counting the odd numbers. That means we have the probability of the primes at the end, 2 over log x approximately, log n, 2 of those, and then 1 minus 2 over the probability, but there's not k minus 1 of those, there's actually k over 2 minus 1. So in this example, we've got a prime gap of 1, 2, 3, 4. So 4 over 2 is 2 minus 1, because there's only 1 in the middle that could carry the probability. So that's how we arrive at a new expression for the probability of gaps of size k when we have excluded the evens. And that's where those 2's come from, and the k minus 1, that's another error I need to fix. Great, so I've fixed that. It's good to spot these errors as you go along. Right, so overall it's a similar sort of structure to the previous one. It's just a few factors that have changed. And we're multiplying it by n over 2 approximately, because we're only applying it to half the numbers in the range up to n, because we've excluded all the odd numbers. Right. Let's see what graph that gives us if we plotted that, if we took the log and then plotted that against the gap size. There you go. So this new chart, this new graph of this slightly improved model works really well for smaller gaps. So this is, say, up to gap sizes of 75, 80, works really well, even almost up to 100. That's not bad. It's quite a good fit there. For larger gaps it goes wrong. I mean, there is one there that it does touch. I think that's 282, so it gets that one right. But broadly, it's both of those simple models aren't doing very well for very large gaps, and that's well known. The exploration of the distribution of large gaps is an active research area. But it's really nice to see that such a simple improvement, such a simple improvement in the model gives us such a good result experimentally. That's really good. So that's just a taster there of how we can use probability and probabilistic models to model the primes and see what kind of predictions that makes. It's interesting, just for fun, to watch the prime gaps grow as capital N grows, and compare them with these two models. So there's a little YouTube link there. I'll play it now so we can see. It's only 60 seconds or so. Now, before we finish, we should kind of just challenge ourselves and say, well, what have we really learnt? Was that linear form of the log count very special? And if you think about it, it wasn't really, because any independent event, when we think about sequences of them, they result in the same linear log count. If we were tossing coins, for example, if we wanted, say, to model the number of chains of all heads or all tails in a long sequence, say if you had 100 goes and we said, okay, how many chains of all heads of size 2, 3, 4, 5 do we get? We'd end up with the same linear expression when we think about the log of the count. So that's not special. That's not special to the primes. That's just what you get when you model sequences of independent events. What does it tell us though? Well, it suggests that the primes kind of occur fairly randomly as well. Let me rephrase that. They don't occur with a particularly skewed distribution, because if they did, then this plot would not be this shape. This linear plot happens when the events are almost random. If the distribution of primes was interestingly skewed, not random, or very not random, we would not have that distribution. So that's probably the most we can read into that, which is still interesting. And the fact that the order of magnitude, this kind of intersecting at around 18, I think, and over here at well, it's slightly more wrong over here, but it's not wildly off. That tells us that the basis for this model, the prime number theorem derived probability, is about right. So that's what we can learn from doing that. So I hope that's been an interesting diversion for you. It's just a different sideways look at prime numbers using probability. I first thought, well, this isn't going to be very fruitful because probabilistic models are going to be an oversimplification. So I've been quite surprised at how good the results have been. And if you do read more about it with much more sophisticated techniques, you'll find that some of the results that are produced from probabilistic models are really rather reflective of reality, and that's quite amazing. Ooh, before we go, this is just a chart to compare what would happen if we were doing coin tosses with probability half head, half tail. So you can see it's a straight line there, just for completeness there, and you can go and play with that yourselves. Hope you enjoy that. We'll see you next time. Bye.